Gravity pulls things together, always, without exception. Every piece of matter in the universe attracts every other piece. That's the rule, confirmed across centuries of observation, built into the most successful physical theory ever constructed. So here's what should be true. The universe's expansion, set in motion by the Big Bang, should be slowing down. The collective gravity of all matter, pulling on all other matter, should be acting like a brake, not stopping the expansion, but decelerating it, making it slower over time. In 1998, two independent teams of astronomers set out to measure exactly how much the expansion was decelerating. They found it wasn't decelerating at all, it was speeding up. The universe is expanding faster today than it was 1 billion years ago, faster tomorrow than today. Something is driving the expansion to accelerate, pushing space apart across cosmic scales, overpowering gravity, growing stronger as the universe grows larger. We have no confirmed explanation for what it is. We called it dark energy. That name isn't a discovery, it's a label we attached to our ignorance so we could talk about it in papers. The story of how we found it is worth telling precisely because the precision is what makes it convincing. Type 1a supernovae are stellar explosions, a specific type triggered when a white dwarf star accretes enough mass to exceed a critical threshold and detonates. The peak brightness of these explosions is nearly uniform, the same intrinsic luminosity, event after event, across the universe. This makes them standard candles, objects of known brightness that can be used to measure distance. If you know how bright something actually is, and you measure how bright it appears from Earth, the difference tells you how far away it is, precisely. The Supernova Cosmology project and the High Z Supernova Search Team were competitors, separate teams, separate data, the same goal: measure how much the expansion was slowing by comparing nearby supernovae with distant ones. The distant supernovae came back fainter than expected, fainter than they should have been if the universe's expansion was decelerating. Fainter because they were farther away than expected. Farther away because the universe had expanded more between then and now than the deceleration models predicted. Both teams got the same answer. Neither trusted it initially. They spent months looking for errors, systematic problems with the data, calibration issues, dust obscuring the distant supernovae. The results survived every check. The expansion is accelerating. Confirmed. Independent teams, multiple cross-checks, and in 2011, the Nobel Prize. What they found wasn't an answer. It was a question written across the entire visible universe. Let's be precise about what acceleration means here, because it's not just expanding faster. Gravity is universally attractive. Every piece of matter pulls every other piece toward it. For the expansion to accelerate, something must be producing an effect that acts against gravity on the largest scales, not between objects, but on space itself. Something that drives space to expand faster, not slower. And here's the part that makes it genuinely strange. Whatever this is, it doesn't dilute as space expands. Normal matter dilutes. When the universe doubles in volume, the density of matter drops by half. The same amount of stuff spread across twice the space. Energy in radiation dilutes even faster. This is basic physics. Dark energy doesn't dilute. The energy density, energy per unit volume, stays constant as the universe expands. As space grows, the total amount of dark energy grows with it. More space means more dark energy, which drives more expansion, which creates more space, which contains more dark energy. This is not behavior any known substance exhibits. Matter doesn't do this. Radiation doesn't do this. Dark energy, whatever it is a fundamentally new kind of thing, if it's a thing at all in any conventional sense. There's an old idea that fits the data almost perfectly, and the history of it is worth a moment. In 1917, Einstein was applying his general relativity equations to the universe as a whole. The equations predicted a dynamic universe, one that should be expanding or contracting. Einstein believed the universe was static, eternal and unchanging. So he added a term to his equations, the cosmological constant, lambda, a fixed energy density of the vacuum built into the geometry of space-time, whose effect exactly balanced gravity and kept the universe static. When Hubble discovered the expansion in 1929, Einstein discarded lambda, called it his greatest blunder. In 1998, lambda came back. Dark energy behaves exactly like the cosmological constant, uniform density, constant over time, causing accelerated expansion. The mathematics fits beautifully. Lambda, reinterpreted not as a device to hold the universe still, but as an intrinsic energy of empty space, is currently the simplest and best fitting description of dark energy we have. But here's the critical distinction. Fitting the data mathematically and explaining what it is physically are completely different things. Lambda says, empty space has energy. It doesn't say why. It doesn't say what that energy is. It doesn't connect to any other theory. It's a number in an equation, extraordinarily well confirmed, completely unexplained. And when you try to explain it, that's where physics hits a wall unlike any other. Quantum field theory, our best theory of particles and forces, predicts that the vacuum isn't empty. It's seething with quantum fluctuations, virtual particle pairs flickering in and out of existence, constant and unavoidable. This isn't speculation. It's confirmed experimentally through phenomena like the Casimir effect, where two uncharged metal plates, placed very close together, experience a measurable attractive force due to the vacuum energy between them. The vacuum has energy. We've measured effects of it directly. Quantum field theory also makes a prediction for how large that vacuum energy should be. And here's the problem. The predicted value is somewhere between 10 to the power of 60 and 10 to the power of 120 times larger than the observed value of dark energy. Let that sit for a moment. The worst prediction in the history of physics, by a margin that dwarfs every other discrepancy in science, a theory that works with extraordinary precision in every other context, produces a number for the vacuum energy that is off by at least 60 orders of magnitude, possibly 120. Something must be cancelling almost all of the vacuum energy, reducing it from its enormous predicted value to the tiny observed value. What is doing the cancelling? Why does it leave just enough to produce the observed acceleration and not more or less? We have no answer, not a partial answer, not a leading hypothesis, no answer. This is the cosmological constant problem. It sits exactly at the boundary between quantum mechanics and general relativity, the two pillars of modern physics that we have been unable to unify. The cosmological constant problem may be the clearest signal that something fundamental is missing from our understanding of both. Before going further, let me clear up a confusion that comes up constantly. Dark energy and dark matter are not the same thing. They share the word dark, meaning undetected, unexplained, and nothing else. Dark matter clusters. It congregates around galaxies and galaxy clusters, providing extra gravitational pull that keeps them from flying apart. It interacts gravitationally with normal matter. It makes up about 27% of the universe's total energy content. We know it's there because of what gravity does. Galaxy rotation curves, gravitational lensing, the large-scale structure of the universe. We don't know what particles it's made of. Dark energy doesn't cluster. It's uniformly distributed through all of space, in galaxies, in voids, in the spaces between atoms. It doesn't provide gravitational attraction. It drives the expansion of space. It makes up about 68% of the universe's energy content. Normal matter and energy, everything physics has ever described, detected, explained, or built technology from, makes up the remaining 5%. 5%. The standard model of particle physics, quantum electrodynamics, the entire periodic table, every star and planet and galaxy, 5% of what exists. Dark energy may not be constant. This possibility matters enormously, and it's live right now. The cosmological constant assumes lambda is fixed, the same energy density everywhere for all time. But there are theoretical alternatives. Quintessence is one, a dynamical scalar field similar to the inflaton field that drove the universe's early inflationary expansion, that fills all of space and slowly evolves over cosmic time. If dark energy is quintessence rather than a cosmological constant, its equation of state, the relationship between its pressure and energy density, would vary. That variation would leave measurable imprints on the expansion history and the large-scale structure of the universe. In 2024, the DESI collaboration, the Dark Energy Spectroscopic Instrument, released results from the largest galaxy survey ever conducted. The data showed possible hints that dark energy may not be constant, that it might be evolving over cosmic time. The signal is not yet statistically definitive. It could be a fluctuation in the data, but it could also be the first observational evidence that lambda is not the right description. If confirmed, this would change everything. A cosmological constant is something you measure and accept. A dynamical dark energy is something you need to explain with a physical field, a theory, a mechanism. The physics community is watching this result closely. This is not settled science. It's science in progress, which is exactly where the interesting things happen. What happens to the universe if dark energy continues? If lambda is constant, and current data is consistent with this, the universe expands forever. Gradually, galaxies beyond our local group recede past the cosmological horizon, vanishing from our observable universe. The cosmos becomes increasingly cold, dark, and empty over unimaginable timescales. Our local group of galaxies remains gravitationally bound, an island in an accelerating void. If dark energy strengthens over time, a scenario called phantom energy, the outcome is more dramatic. The repulsive effect eventually overcomes gravity at smaller and smaller scales. Galaxy clusters tear apart, then galaxies, then solar systems, then eventually, in what's called the Big Rip, The expansion becomes so violent that it overcomes the electromagnetic forces holding atoms together. All structure in the universe, down to subatomic particles, is destroyed in a finite time. Current observations do not favor the Big Rip. The cosmological constant model predicts a gentler fate. But we don't know what dark energy is. We don't know if it's truly constant. We cannot rule out scenarios that end everything. And we won't be able to until we understand what we're dealing with. Let me be precise about what we actually know. The acceleration of expansion, confirmed. Multiple independent methods, beyond reasonable doubt. Dark energy comprises approximately 68% of the universe's energy content, confirmed by CMB measurements, supernovae, baryon acoustic oscillations, large-scale structure. Dark energy behaves like a cosmological constant to within current precision, confirmed. What dark energy is physically, unknown. Why it has the value it has, unknown. Why quantum field theory's vacuum energy prediction is wrong by 10 to 120 orders of magnitude, unknown. Whether dark energy is truly constant or slowly evolving, unknown, possibly being tested right now by DESI. The name dark energy describes what it does. It does not describe what it is. Naming is not understanding. This is one of those cases where the distinction matters more than usual. 68% of the universe, the dominant component of everything that exists, actively determining the fate of all matter, all structure, all life, completely unexplained. The theories we're most proud of, quantum mechanics, general relativity, the Standard Model, describe 5% of what the universe contains. The other 95% is dark matter and dark energy, two labels on two gaps, sitting quietly in the equations, refusing to reveal themselves. This isn't a failure of physics. It's a map with most of the territory still blank. And blank territory, the places where the equations run out and the observations demand something new, that's where physics lives when it's doing its most important work. The universe is accelerating toward a future we cannot fully predict, driven by something we cannot explain, at a rate determined by a number whose origin remains one of the deepest unsolved problems in all of science. And we're the species that noticed, that measured it, that named it honestly as ignorance. That, I think, is where we should start, not end.